you just have to remember that you have to take a cross product for magnetic force and then electric field part as the electric force, right? Electric force, magnetic force combined, those are called Lorentz force, right? And can you tell me that if there is no external field, then what would be Lorentz force? What would be Lorentz force if there is no external electric field? Yes, if there is no external field,
Sir, if there is no external field,
yeah, then external electric field, then what
there's
would
no.
be, yeah, then what would be your Lorentz force? No electric field, which means E is zero. Then what would be your Lorentz force?
Sir, Lorentz force will then be.
So if electric field is zero, then what it implies? That your force electric, that would be zero. So
Yes, sir.
Lorentz force is this plus this. So this is zero. So Lorentz force would only be magnetic force. And similarly, if you are you have a charge which is in the, yeah, so it doesn't have a magnetic field around it. So then your B is zero and magnetic force is zero. Then this Lorentz force would be only, these are the simple things, right? Okay, so now let us move on to the magnetic force. Magnetic force due current carry conductor. Right. So, and this is a linear wire. Right. So let's say you have this wire, and some current is flowing through this one. Let's say I current is, and then you want to calculate the magnetic force at this point. Right. So what would be the magnetic force at this point due to this current carrying conductor? So this is simply I, and let's say this is I, this then is L, and whatever the magnetic field is, right? Then whatever magnetic field is, this would be right at this point. So the magnetic force would be simply I and L cross right. So this would be the magnetic force. This length is right. This length is the separation between the wire and the point that we are talking. So that would be magnetic force, right? So is it clear to you? Is it clear? Yes. Is it clear to you, Archana?
Yes, sir.
Yes. So this is the magnetic field, and if this length, right? If this length is right, if this length, so if this length is perpendicular to this magnetic field, right? L is perpendicular to magnetic then what would be the magnitude of this magnetic force? What would be that? So this would be I LB sine theta. But the angle between L and B, that is 90 degrees, right? So this is ILB and sine 90, and sine 90 is how much? That is 1. So this is simply ILL. Right, so this would be the fact. So is it clear to you? Yes, is it clear? Yes,
Yes, sir.
yeah, so this would be the magnetic right. Yeah, I have a doubt that if we have this conductor, right, and the charges are moving, right, so this is Q cross V, right, and this would be VD. So VD is and then Q is the total charges in the cross the total charge is the what n into what cross the n. Okay, so this should be right. So this should be yeah, and the n q cross the a g. This is the n a b. So I l cross a. So this l is this length. Okay, yeah. So this is not this length. So that is what I was confusing. This length is there. So if you have a current carrying wire, right, and this is placed in some magnetic field, right? So let's say some magnetic field is there. Then what would be the magnetic force experienced by this thing? Right, magnetic force experienced by this conductor. So the length is this one. So length of the conductor. So this is the length that I'm talking. Right. That is in the direction of the current. So you have to take this in the direction of the current. Okay, clear. So this would be the length. Length would be this thing, and it has some current which is flowing in this direction. So this would be IL cross. Is it clear to you? Yes,
Yes,
Arjun.
sir.
Yeah. So where are you?
Sorry, sir. I'm just very tired, sir. Can't focus at all today.
Not. Yes,
Yes,
boss.
sir.
Focus is needed,
Yes, sir.
right? So what did you do today? Oh, you are not well, right? What is happening?
No, sir. Today there was school also, and I had to go even when I was sick because we had to fill that TC letter, right, for school.
Oh, oh, so yeah. What about your farewell thing? What happened to that?
It's a farewell happened, sir.
It happened.
Yes,
When did
sir.
it happen? 2 days back.
So on 2nd February,
Oh,
February.
2nd February. Oh, so yeah, 2 days back, right?
Yes.
Okay, yeah. So did you got your signature, yeah, signatured shirts? Or
No, no,
get
sir. I think so. We got shirts and all. We just got mementos, gifts, and all that, sir.
oh, mementos. But you want to remember your friends, right? So
Yes,
those shirts are the mementos, right?
yes, sir.
So yeah, because whenever you will look at your shirts, then you can remember those signatures of your friends, right? Yeah. Okay.
Mm.
That is that not allowed in your
No, sir, it's allowed. It's allowed.
signature? Oh, it's allowed, but you didn't do that.
Yes.
Because yeah, I got the signatures of yeah, every class members of mine. So, yeah, I roamed
Yes.
around and then I forced everyone to sign that. Our school was co-ed school, and yeah, I forced everyone. So that was the first time that I talked or yeah, everyone. Yeah.
Yes, sir.
Okay, so this is the magnetic force in a
Hmm.
current carrying wire, right? So this is the okay. And what is the direction of this force? So the direction of this force is length into the cross product of length and magnetic field, right? The length of the wire and the magnetic field. So this is the magnetic force. Now, what would be? So there is an important thing which is the force force between current carrying wire. Right. So we have to find out the force between current carrying and they are parallel wires. So this is a very important. So this is very important, right? And this will give you the definition of the 1 ampere current. So whatever definition you know about the 1 ampere current, that comes from this thing, right? So you have wires, right? And the current is right. The current is moving in the same direction, right? And let's say you take the this part, so this length of the wire. Let's say this is length is L, and the separation between the two wires, that is R, right? And before we do this thing, right? Before we do this thing, you have to remember, right? You have to remember that what is the force, magnetic force due to a current carrying conductor. That is I and cross. This thing you have to remember, right? So this L is the length of the wire. Magnetic field is the external magnetic field, and then you have this current which is flowing through this wire. So remembering this thing, and you have to remember this thing as well. So you have this wire, and current is flowing. So, do you remember what was the magnetic field of this wire at this point? Do you remember that? What was the magnetic field due to this current carrying wire? Yes. Do you remember it?
So magnetic field of a
Magnetic field of a linear current carrying wire. So, you have a linear current carrying wire. So, what is the magnetic field at certain distance? Let's say this distance is r. So what is, and let's say this is the I1 current, this is I2 current. Yes,
so
go on.
then isn't
What is BP due to this wire? This is a very important.
sir like pi r something 1/2 pi r?
Is something like mu naught
Yes,
I
immune.
by 2
Um,
pi.
yes, sir.
That
I by
was
two.
this was the magnetic field. You have to remember these things, right? These are
Yes, sir.
so please go and revise because you know Ampere circuital law, right? So you can quickly draw an Amperian loop, and then you have this I current. So B dot dl integration, that is your mu naught I. So I enclosed is I, and then this area is B into pi r, so mu naught I. So you'll get B as mu naught I by 2 pi r. That is how this Ampere circuital law that is very useful, right? If we don't remember, then we can apply this thing and then we get right. So please, yeah, first four chapters they are very crucial, right? So magnetic. Now you remember that magnetic field is mu naught I by 2 pi r at this point. Can you tell me that what is the direction of magnetic field at this P point? What is the direction?
Sir, at which point, sir?
At P point, what is the
Mm.
direction of magnetic field due to this current?
Sir, it will go at the same direction as R, like around the current I.
So you are saying that this magnetic field is upwards.
No, sir, it's the so what's the direction of the current?
Direction of current is upwards.
Okay, fine, sir. So
What
the
would be?
magnetic field will be around the current carrying conductor I, right?
Yeah. What is the magnetic field at this point? This is the question. Yes, this is the question. So we have to use the
Sir,
Maxwell's thumb rule.
yes, sir, I'm using that only. So,
So you
won't
point your thumb,
yes, sir, so
point.
perpendicular, right? Like to the
So So if you point your thumb and then place curl your fingers in the direction of P, so you're getting inside,
oh
inside
inside
the
like
P.
that, you know.
So this would be cross.
So
Yes,
inwards, right? In that
inwards,
sense.
inwards,
Yeah, yeah,
inwards.
yeah, inwards.
What you were telling me, right? You were telling me around the wire. What is around the
No,
wire?
sir, I meant it. I don't know how to use the proper word. I didn't know how to use the proper word for it, sir. Essentially, I meant that it was
Oh,
going inwards, but I didn't know
inward.
how to say it in that sense.
So we have to be very careful with those technical terms, right? Because
Yes,
because
sir.
science and the technology, right? Science and tech for everything, right? So yeah, so this would be inverse, right? And yeah, you meant to say that this loop direction. That is what you were saying.
Yes, sir. So,
Okay.
essentially that.
So that is that is correct. That would be it. So, but in here this would be inside. Yeah. Okay. So we know that magnetic field is inside. Value is this thing. Good. So if we remember that, so magnetic field. Let me draw the magnetic field. So I am drawing the magnetic field due to I1 current at these points. So this would be the magnetic field, right? At each and every point. At each and every point, this would be magnetic field. Clear box.
Yes, sir.
So this is magnetic field. And then in this wire, the current is flowing I2, right? The current is flowing I2. And the length that we are taking is L. So what would be of magnetic force on 2 due to 1? What would be that? Yes, what would be that? So that would be I L cross P, correct?
Yes, sir.
Yes, clear.
Yes, sir.
Okay, so length is what is the direction of length? This is upwards. Length is upwards. What is the direction of magnetic field that we have just discussed? What is the direction of magnetic fields? Let me write it as. So this would be I2 and
Mm.
yeah.
Yes,
So
sir.
what would be the direction of magnetic field?
So that will be inward side. So
Inwards. Good. Inwards is the direction of magnetic field, and upwards is the direction of length. So L is J hat, correct? And magnetic field direction, that is what?
hmm.
Yeah.
So that
So
will be K hat.
K hat. So inwards is K hat, outward is minus K. That is what you are implying.
Yes, sir. So inwards is
Outward,
minus.
yeah. So you confirm yourself, right?
Yes,
What
sir.
would be?
I forgot inwards and outer. Which one it was? Sir?
So minus K. Yeah. So you are correct. So this is now we will need this to find out the direction of the force. But as of now, we will try to calculate the magnetic. So what is the angle between L and B1? That is 90 degrees, right? Theta
Yes,
is
sir.
90 degrees. So you have magnitude. This is I2 L B1 sine theta, and this is 90. So this is simply 1. So F21, that is simply I2 LB1. And we have just discussed that what is the value of this B1, right? We have just discussed this. So magnitude of B1, this is mu naught I1 by 2 pi. So if we write it, or if we simplify this, write it properly. So this is mu naught I1, I2, L divided by 2 pi m. And let us remove this subscript, right? So this is your force experienced by the, and this, so due to this current as well, there would be same magnetic force on this one, same magnetic force. And now let us talk about the direction. What would be the direction? So direction is, so this is magnitude, right? Magnitude. And let us talk about the direction. So how can we calculate the direction? N hat, this would be L hat, B hat. So L hat is J hat, B is minus K hat. So minus we can take common. What is J cross K? What is J cross K? What is J cross K, boss? Yes,
I.
I have
Yes, sir.
I, J, and K, and you go in circular direction. So J cross K is that.
Yes, sir.
So this is the direction of force. So remember this force is on 2 due to 1, and minus I hat is which direction? Can you tell me what is minus I hat direction? Right hand side, left hand side. What is the direction? Minus
Left
I
hand
hat,
side.
left hand side. So this is the direction of force on 2 due to 1. Right? So this is the direction minus I hat. So this is telling us that what kind of force is acting, repulsive or attractive. Yes.
Yes, sir.
What kind of force is acting? Repulsive or attractive? Yes,
Mm, so repulsive force?
repulsive. So this wire is attracting this. The force is towards each other. So towards
Hmm.
is attractive or repulsive.
Towards is attractive, sir.
So force is attractive, right? Force is
Yes.
attractive. So this I1 is trying to pull this thing, pull this wire, parallel wire towards each other. And similarly, this thing is also applying the same force. If yeah, again process or do the same calculation, so we'll get that relation as well. But we will not do that thing. And yeah, now from analogy, we can write that this is F1. These forces are equal, and I'm writing just the magnitude as F. So you can write that F12 that would be equal to minus of F1. So those are equal but in opposite direction, right? You see that this one is this direction, this was in this direction. So they are equal but opposite. So this is the force between current carrying wires, and this force, if so to what is here to note that the force, right? So force is attractive if the current are flowing parallel. So what do I mean by that? We saw that both the currents are in same direction. So that is why I am calling it parallel. But the thing is to remember that force is repulsive if the currents are flowing anti-parallel, right? So if you have these wires and they are flowing like this, so this one is going up, this one is going down. So in this case, magnitude would be same. This is mu naught I1, I2, and L by 2 pi r. But the force would be repulsive. So this from this one the force would be in this direction. From this one the force would be in this direction. So force would be repulsive. Clear? For anti-parallel. Clear? Is it clear?
Yes, sir.
Okay. So now definition of one, and this can be asked. So this is definition of one and that is totally dependent upon this the force between two parallel lines. Right? You please note down these two things, and then we'll talk about the definition of one. Please note it down. And whenever you want me to scroll down this,
Yes, sir.
yeah,
Noted down, sir. Give me 30 seconds, sir. No finish this.
yeah, yeah. So don't go asleep in the class, right? While noting it down, don't go to sleep.
Yes, sir, done.
Done. So then, please, down. And this is very important. Okay. So if you have a slightest bit of doubt in this one, please ask me again. Yeah. Whenever you have noted it down, please.
Yes, sir, done.
Yeah. Then please,
Yes, sir, done.
done. Okay. So now let us study about the definition of an MP, right? So what do we know about right? So before we do that, let us quickly write. Right. Let us quickly write that. So we have two wires, right? Then let's say same current I is flowing through these wires, and the separation between them is 1 meter, right? And the force, so let's say that what would be the force, right? First, let us go back to this thing. I will write it in here. So let's say you have this wire, right? And this is the separation between them is R, I1, I2, and the length that you take is L. So force is how much? That is mu naught I1, I2 divided by pi r, and then this is L. So this is what we got, right? Right.
Yes, sir.
So if I take this L in the left hand side, so what would be this thing? This is F by L. And this would be simply mu naught I1, I2 divided by 5, right? So this would be, this is called, let's say small m. And this is mu naught I1, I2 by 5. And this is called, so this is force, this is length, and this is a division. So this is called a force per unit length. And this is simply this quantity. And what would be the unit of this thing? Unit would be Newton per meter. So this is the preliminary for the definition of 1 ampere. Is it clear to you? Is this thing clear? Yeah, is this thing
Yes, sir.
okay? So what we are taking is that you have 1 meter, 1 meter separation. Current I is 1 ampere. This is 1 ampere, and then you have force per unit length, right? So what would be force per unit length for this thing? So F would be mu naught and I into I divided by 2 pi, and R is how much? R, right? So this would be your force per unit length, and I is 1, this is 1, so this is mu naught, and this is 1 into 1. This is 2 pi, and R you have taken 1, right? Clear? Is it clear?
Yes, sir.
So this mu naught value is how much? What is the value of mu naught? What is the value of mu naught? So you remember
So
mu
mu
naught,
naught is equal to mu naught by 2 pi. So
eh?
23 point.
I am
Uh,
asking the value of mu naught value.
yes, sir. Mu naught value is equal to F by 2 pi.
This is a
F
constant
into 2 pi. Oh, yeah, mu
for
naught.
which
Okay.
you 4 pi into 10 to the power
No,
minus
yes, I
7.
forgot. I forgot. Mu naught.
This is the value, right? So if you put this value, 4 pi into 10 to the power minus 7, and then you divide it by 2 pi, so what you are getting? You are getting 2.
2
So
pi.
this is 2 into 10 to the power minus 7 Newton per meter. This is the force per unit length, right? So this is the force per unit length experienced by these two wires. Is it clear?
Yes, sir.
So, and what was the value of current that we took? 1 ampere. So from this thing, the definition of 1 ampere is defined, right? So you give the definition of 1 ampere. So 1 ampere is defined as the force per unit length to force per unit length or so 1 ampere is defined as the current flowing between two wires having equal magnitude and same direction and their separation is how much is the separation between the wires? Remember, as you have derived this in just a moment ago. So what is the separation that we took?
Uh,
Uh,
750 centimeters.
Separation is 1 meter and the magnitude of force per unit length is 2 into 10 to the power minus 7 10 per meter. Right. So let's say you have two wires, right? And you have a device with which you can calculate the force. So what you do is that, and you can calculate force per unit length, right? So you take 1 meter or whatever length of the wire, and then you measure the force per unit length. And those wires have separation of 1 meter each. And the current that you are passing between the wires is the same, right? And then if your value is showing that the force per unit length is 2 into 10 to the power minus 7 meter, then you can say that the current flowing between these two wires is 1 amp. So is it clear to you? Did you
Yes,
understand
sir.
me? Yeah. So let's say somehow you are measuring the force per unit length between the wires, and then the separation that you make between the wires is 1 meter, and then you measure it, and then you fix it, or you you tune it, right? You tune it to the value this much. So you tune it your force per unit length in such a way that you achieve this value. Then the current which is flowing through those wires, that would be 1 ampere. So that is how the 1 ampere current is defined. Right. So that is totally related with this force per unit length. Right. So you please note down this thing. Please note down this thing, the prerequisite, the preliminary idea, what is force per unit length, and then you note down the other things. I will write it force per unit length. Please first note down this thing and then after put that definition of quantity. And this is very crucial, right?
Yes, screw.
Yeah, so then please yeah,
Yes,
whenever you
sir.
have done, okay, you have noted this part as well.
One second, sir. Yes, sir. Done.
Okay. Then let us talk about the magnetic magnetic moment of current carry. Right, so let's say if you have let's say this is there, and current is flowing like this is A, B, C, D, and the current is flowing like this, right? So then the magnetic moment of this thing, right? Magnetic moment of this thing would be in this direction because this is so this is defined as magnetic moment is defined as phi a, right? So this is in the same direction as the area vector. So if you are taking A, B, C, D, so this would be this direction, left. And if you are taking C, B, A, D, so that would be your right, right? So this is called the magnetic. And if you have a loop which has n turns, right? So let's say if you have a loop which has n turns, so if it has n turns, let me write it this way, n turns, then what would be the magnetic? Then magnetic moment is simply n I, right? And this is similar, quite similar to your dipole. So what was the dipole moment? Dipole moment was P, and this was QD, right? So Q and separation between the charges. So this was the dipole moment, but in the case of magnetic field, you have magnetic, right? So this was dipole moment, and this is magnetic. And this is very crucial in defining the galvanometer, right? So we can understand the working principle of galvanometer through this magnetic moment, right? Because the force, right, the force on a current carrying loop. So the force on a current carrying loop, force on a current carrying, this is 0. F net is 0. So let's say if you have this loop and you are calculating the force due to this loop, right? Then this would be 0. So F net would be 0 for this loop. Okay, because F net would be how much? That would be, let's say this is A, B, and D, and let's say this is FAB, and this is FBC, and this is FCD, and this is FDA. So all these, so FAB is and FCD. Those are in opposite direction. So they will apply the force in opposite direction. But the magnitude of those forces would be the same. So this one and this one will cancel. This one and this one will cancel because those have equal and opposite forces. All this one will cancel each other out and will get 0 force. So net force due to a closed loop, that is 0. But there would be a torque in this loop, right? This torque would be how much? So torque due current carry, and this is how much? So this is represented as tau, and this is. Do you remember? For the case of electric field, what was the torque? Do you remember? What was the torque for the case of electric field? What was the
For the
torque in a,
case of
yeah, in a torque in a dipole? What was the torque in a dipole? Do you remember it?
torque in a dipole, so so Q D sine theta, something like that, right?
QD was dipole, right? So this was P
Q
cross
E sine theta. So,
PE sine theta. That was
yes,
PE sine theta.
yes, P
So
sine
this
theta.
was the torque. Similarly, because we are taking the analogy, so P changes to M, E changes to P. So this would be your torque in an external field due to a current carrying. So these are the things. These are the preliminaries to understand the action of galvanometer, right? So please note down these things, and then we'll talk about the galvanometer, moving while galvanometer. Yeah, whenever you want me to scroll down the screen, please tell me. So today this chapter would be over. Fifth chapter I will give you. So are you going to the revision classes by Amna? Are you attending that?
No, sir.
Okay, so yeah, you would be given some link to it. Please attend.
Yes, sir. Screw. Yes, sir. Done.
Done. Okay, so the next thing that we have to understand is moving coil galvanometer. And this one is again an important topic. Moving coil galvanometer. Because this has a very wide range of right. So moving coil galvanometer is used to detect the current. It is also used to balance the Wheatstone bridge. It is also used to make an ammeter. It is also used to make voltmeter, right? So this has a lot of purposes, right? But what is how this moving coil galvanometer works? So before we do that, do you remember those telephones? Those have those circular dials. Do you remember that? The old
Yes, sir.
tele, yeah, the old telephones that was like my drawing is bad. Okay, this is a bad drawing. But these had these kind of numbers in circular thing, right? And then you had to rotate this thing, right? And then it will go back to its initial position. Do you remember those dials in the 90s or in the 90s and
Yes, sir.
so those
Probably the other.
yeah, so in the old movies we have seen those telephone dials in which they had to roll those dials, right? They have to, they don't push the button, they have to roll those dials. And you roll those dials in this way, right? Let's say this is 2. So you roll this 2 in this way, and then it will again come back to its initial position, right? So do you get the picture? Yeah, are
Yes,
you
sir.
getting? Yeah, so that is the same thing, which is, so what is happening to this dial, right? What is happening to this dial? So I am applying a torque. I am applying a rotational torque. But a restoring torque is also applied to get back its initial position, right? So if you remember, what was the restoring force in spring constant? Let's say you have this spring, right? And then you have this mass. So if you pull this mass in this side, if you move this mass in this side, so there is a force which is acting in this side, and this was the restoring force, right? Do you remember this thing? So this is the restoring force which was acting for the linear motion or for the linear displacement, right? But
Yes.
you are displacing this thing angularly. So there would be an angular torque, angular restoring torque. So you remember that this restoring force was minus kx, right? So can you identify that what would be, let me write it this way. So can you identify that what would be the restoring torque? What would be the restoring torque? In if I write it in this manner. So what would be the restoring torque? Just taking the analogy from the linear motion. What would be the restoring torque? So remember, you are displacing the object angularly. So you are making an angular displacement. Then what would be the restoring torque? Just take the analogy from this.
Yes, that will be restoring torque. So, like bringing it back, like
Yeah, so that is
return
the
the object back to like its original state.
its
So, like,
original state. Yeah, so that is the restoring torque. But what is the displacement that we are making? Right? You see that this restoring force is
yes,
directly proportional to the displacement that you are making. But this is a spring constant that is there. Yeah, that is there. But you are displacing this thing by this x displacement.
hmm.
So then, what would be if we take the same analogy in here? What would be the restoring torque? That would be k, of course. But what would be there in place of x?
So that will be zero, right? Because the displacement is zero as it's going back to its original position.
No, we have displaced this thing in here.
Uh-huh.
Then some force is acting. Some force is acting.
So that will make an angle, something.
So yes,
Theta, yeah.
phi, theta, yeah, theta, phi, whatever. So that would be angular displacement. And obviously this would be negative, but we ignore the negative side. Right? Is it
Yes.
clear? Okay, so yeah, these are the things that we need in moving coil calculator. So same principle. Whatever we discussed so far, so same principle. Right. So what is the geometrical construction? You have some permanent magnets. You have this permanent magnet. This is north, this is south. Right, and this is a cylindrical. So in here it is looking like a spherical one, but this is a cylindrical. So this is something like those magnets are there, and this is a cylinder. So you are seeing the cylinder from side, right? Actually, this is like this thing, but you are seeing this cylinder from this side, right? So that is why this is looking like a circular thing. Okay, so this will have, and then what you do is that you attach, so you make some turns in this coil, right? In n turns you make, and then you attach some spring to this, right? So if you, and let's say you connect, you have this scale, and those angles are right written in here. Those angles are written here, and you have these this pointer, right? So what you do is that you move this spring, and the magnetic force is directing radially to this, right? So it is going radially from this thing. So magnetic field is radial, and you have these permanent magnets, so your magnetic field is constant. Magnetic field is constant. This area, the surface area, this is also constant. And then what you are doing is that you are passing some current through this thing, right? So you are passing some current through this coil. So your I is also constant, and it has n turns. So you have n turns, right? This you can change. So number of turns you can change. So what will happen is that if you rotate this spring in some direction, so it will try to revert back to its initial position. You are changing the angle, right? You are changing the angle, you are rolling this cylinder, so it will get back to its initial position. So the restoring tool, right? So what is the working principle? So working principle, so it is based on restoring torque, right? And what would be the value of this torque? So this torque we have understood. That is in the previous part. So torque is mb. And because this magnetic moment and this magnetic field, they are perpendicular to each other, so that would be simply mb. Right? So this is simply mb sine theta. And theta is 90 degree because the magnetic moment and magnetic field, they are perpendicular to each other. So this tau is m. Can you tell me that what is this magnetic moment? We have just studied. So we have n number of turns, then I current, and then E. So this is the torque, right?
Yes, sir.
And remember, this should be equal to the restoring torque. So what is this value? What is this value? Yeah,
K theta.
yeah. So this is, let's write it as K5. Because in the standard notation, this is written as 5. So then you can get, right. So then you can get the value of phi as NIA by K, right? So if it is showing zero deflection, then you don't have any current. If it is showing some deflection, which means that some current is flowing, right? Because you have a fixed magnetic field, you have this area, you have this number of turns, and you have this spring constant. So if some deflection is happening through the circuit or through the galvanometer, then we can say that some current is flowing. Is it clear?
Yes, sir.
Okay, so this is the working principle of moving coil galvanometer. Please note it down. Please note it down. And we will stop. So this completes your chapter, right? I will talk about the ammeters and voltmeters as well, but those will not take that much of time. But yeah, we'll stop at this because you are tired and you please look at the proper diagram. For proper diagram, consult. Yeah, whenever you have completed these activities.
Yes, sir. You can scroll down.
Yeah, so that is all right. That is
Yes, sir. I thought you'd do
okay.
something else.
So yeah, we'll stop at here and yeah, see you in the next class. Okay.
Okay, sir. Allah Hafiz.
Allah Hafiz, and yeah, start your preparation, Aslam, right? All the
Yes,
best,
sir.
all
Sorry,
the best.
sir. I just got very tired today.
Yes, no worries, no worries. But yeah, all the best. Start your preparation. Yes, hello, Amna. Assalamu alaikum.
Welcome, Aslam, sir.
Okay, so you wanted to revise the oscillation chapter, right?
Yes, sir.
Okay, so what were the topics that you wanted to discuss? So you have some topics in mind, or yeah, so you have some doubts in your mind that you want, or you want, yeah,
I want that important topics.
oh, important topics. Yeah, so important topics. Yeah, so we have to remember that what is uh, right, what is the displacement for a oscillating wave, right? So for oscillation, what is displacement? For oscillation, what is the velocity? For oscillation, what is the energy? So these are the three things are crucial, right? And we have to remember two very important things. Those are trigonometry